Now, as we know that that after rectification, whether we use PN junctions as half wave rectifiers or we use them as full wave rectifiers, in both the cases we have pulsating DC as output. So, in order to smoothen the output that we obtain from these rectifiers, we make use of circuits which are known as filter circuits. Call them filter circuits. So let us have an introduction of these filter circuits and go with the basic principle of these filters, what we call them as filter circuits. Now, this filter circuit, as I said, it's used to smoothen the pulsating or fluctuating, or pulsating, or you can also call fluctuating output of a rectifier, of a rectifier. So here it should be output. I said my handwriting is very bad, and I'm sorry for that. I can't help that. And the output voltage of a rectifier is unidirectional. That's true, but it does not have steady value. In fact, the output of a rectifier has both AC and DC components in it. In other words, output DC voltages or the voltage of a rectifier has some amount of AC in it, right? And this AC it's basically superimposed on it, on the unidirectional DC that we obtain from rectification. So this AC voltage superimposed on the DC voltage, we call this as a ripple component. So there is some kind of superimposition. There is superimposition of AC on DC that we obtain from rectifiers, and that is known as a ripple component. And we call this thing as ripple component. So there are ripples present in the output that we obtain from these rectifiers. Now, in order to have output voltage of steady value, the AC component certainly has to be filtered out. I mean, a component or a device used to filter this AC component from the output of the rectifier is called as filter circuit. So the component, the component that we make use in the circuit to get rid of these ripples. Okay, so what we call them, we call those circuits as filter circuits. They are also called as, simply called as filters. So can directly call them filters. Now, commonly there are many types of filters that are used. There are capacitor filters. There are circuits in which capacitors are involved. And in capacitor filters, generally they consist of capacitor shunting the load resistance RL. And in case of inductors, we also make use of inductors as filters. And they can consist of an inductor conducted in series with the load resistance. And We can have LC filters, in which we have both inductance and the capacitor, and shunting the load across the load resistance. So, so there are many situations through which we can have filtered output. Filtered output means we will have the rid of these ripples that are present in the output of these rectifiers. Now we can have something like, if we have a pulsating signal that we have obtained, if this is pulsating one, if we make use of a capacitor, and we have a shunted resistance across this capacitor, and known as RL. So here is capacitor C. We will have a smooth output here. So to be simple, and smooth output. So we can have a situation where we have this pulsating output and make use of an inductance, and we can make use of an inductance and have a resistance R in series with this inductance L, and have a resistance RL. In this case, again, the output that we will obtain, we will have smooth output. So these are pulsating signals that we receive from rectifiers, not only from half wave and full wave rectifiers, the other rectifiers which are more efficient, which are highly fast, all of these things, most of these things. And we can have a situation where we make use of both inductance and a capacitor, and we will have an output. I mean, we can have a pulsating DC that I'm talking about, and then we can have an inductance and a capacitor. Okay, so from here we will come up with the output here, and this output will be containing least fluctuating signals. So here we will have smooth output. That's what I was talking about. And there can be many trivial kind of combinations of inductance and capacitors, where we can use them to have better filtration of ripples in the pulsating signals. We can also have a situation like this where we have an inductance and then we have a capacitor here, and then we have another capacitor here, and we have a smooth output. Now the question arises here that how to understand that there is smoothening, how these pulsating signals are filtered out by making use of those filters. So to go with the basics of that, we would like to go with the action of the inductor. Action of inductor. We would try to understand it mathematically as a filter. Now, as we understand that XL is called, what's it called? It's called inductive reactance, if I'm right. It is inductive reactance. The opposition that's offered by the inductance, we call it inductive reactance. And we know that this XL is L omega, right? Now, from this equation, we can we can easily understand for DC, if we talk about DC, for DC, the omega is zero. There is no angular frequency involved for DC. So for that, XL is zero, right? So this inductance will not offer any kind of resistance, any kind of opposition to the flow of DC. Now for AC, if we use the same analysis for AC, so here omega is finite because it has frequency, it has a finite frequency. So if omega is finite, then XL here is finite. What does it mean? It means an inductance offers resistance, it offers impedance, it offers opposition to the flow of alternating current. And on the other hand, it does not at all offer any opposition to the flow of direct current. So from this analysis, the DC component of the output of the rectifier is passed through the inductor easily without any loss, and AC component is blocked by this inductor. So we can understand for AC, it will act as a block for AC components, but for DC, it's an open gateway. It does not offer any kind of opposition to the flow of DC. Therefore, the inductor filters, they reduce the fluctuation. They reduce fluctuation that is present in the outputs of these rectifiers. So I can say that that these filters reduce the fluctuation of the voltage across the load resistance RL that I was talking about. Now, another important thing, another element that we talked about is the capacitor. Now, in case of capacitor, so we would like to see the action of a capacitor, right? So action of capacitor. Now, in this case, we are well aware about the XC. Now, what is XC? That is capacitive. That's capacitive reactance. Capacitive reactance. And this is the opposition part of the capacitor that gives the measure of opposition that this capacitor offers to the flow of currents. Now we have this XC equal to 1 by C omega. Right? Now what is C is the capacitance of the capacitor, and omega is the angular frequency. Now for DC, if I talk about DC, for DC, this omega must be 0. Because it doesn't have any frequency, it doesn't have any frequency. So if omega is 0, what am I going to get here is XC is 1 by 0, and that can be set as infinite. Infinite. Right? So this capacitor will behave as an open circuit for the DC. It won't allow any DC to pass through it. But at the same time, if I go with the AC, what's going to happen is we will have omega, and this omega is finite in case of AC. Now, if it is finite, then XC is finite. So that means the opposition that's offered by the capacitor to the alternating current is finite. So it won't allow it is finite. So it will allow the alternating current to pass through it instead of direct current, because for direct current the opposition is extremely large. It's infinite. But for AC it is 1 by some number, so it's not that its magnitude is small. So so its magnitude is small, so AC can be passed through these capacitors. So that's why in circuits we make use of these capacitors as bypass filters. We use them as the blockers of DC, but they allow the AC to pass through them. And at the same time, the inductors, they block. What they do is for the case of inductors, what we saw was that XL is 0 for DC. That means they don't offer any opposition to DC. So DC can easily pass through these inductors, and for alternating current, these inductors will act as blocks. They will oppose the flow of AC components that are present in the signal. So with this, I would like to end this brief introduction of filters, so that there is an overview to the students for making use of these filters to have better filtration from the outputs that we obtain from the rectifiers that we use.